Here's a deceptively simple-looking equation. E to the x equals x to the x. What makes this interesting is that x shows up in two very different roles, as a base on the right and as an exponent on both sides. At first glance, you might think this is impossible to solve algebraically, but there's actually an elegant path forward. Before we dive into solving this, let's first think about where solutions could even exist. What happens if we plug in x equals 0? Well, x to the x would become 0 to the 0, which is one of those indeterminate forms that doesn't have a well-defined value. So we can rule out x equals 0 right away. What this means is we're only looking for solutions where x is positive. All right, now let's actually solve this thing. The key insight is to use logarithms. They're really good at pulling down exponents and making them more manageable. If we take the natural log of both sides, that's totally fine since both sides are positive. So we get natural log of e to the x equals natural log of x to the x. Now we can use the power rule of logarithms to bring those exponents down in front. Just as a reminder, the power rule says that log of a to the b equals b times log of min a. This turns exponentiation into multiplication, which is much easier to work with. Applying that rule, we get x times natural log of e equals x times natural log of x. Here's where things get nice. Natural log of e is just 1. That's essentially the definition of e. It's the number where the natural log gives you 1. So this simplifies to just x equals x times natural log of x. Since we know x isn't 0, we can divide both sides by x. And we're left with 1 equals natural log of x. To solve for x, we need to undo this logarithm. We do that by exponentiating both sides. So e to the 1 equals e to the natural log of s. Since the exponential and the logarithm are inverse functions, they cancel each other out. E to the natural log of something is just that something. And there we have it, x equals e. Now, finding one solution is great, but is it the only one? Let's look at this from a few different angles. First, let's see what happens if we use a numerical method. We can think of this as finding where the function f of x defined as e to the x minus x to the x equals 0. Newton's method gives us a way to zero in on solutions iteratively. I won't go through the derivative calculation, but let's watch what happens. Starting with an initial guess of 3, the first iteration gives us about 2.811, then 2.7309. And after just a few more steps, we converge right to e. So the numerical approach confirms what we found algebraically. Next, let's visualize what's actually happening with these two functions. If we plot both sides of the equation as separate functions, the solutions will be wherever they intersect. In blue, we have the familiar exponential function e to the x. And in green, we have x to the x, which has a much more interesting shape. Notice how it actually decreases at first, hits a minimum around x equals 1 over e, and then starts increasing. And you can see pretty clearly these curves cross exactly once. If we zoom in, we can confirm that intersection is right at x equals e. Zooming back out, after that crossing point, x to the x starts growing much faster than e to the x. They just diverge and never meet again. Finally, let's think more carefully about why there's only one intersection. Going back to our function f of x, which measures the difference between these two curves, when x is between 0 and e to the x is bigger than x to the x, so f of x is positive. But when x is greater than e, x to the x overtakes e to the x, making f of x negative. The reason x to the x grows faster involves some calculus we won't get into here, but intuitively, when both the base and exponent are growing together, you get this super exponential behavior that a fixed base exponential just can't keep up with. What this tells us is that f of x starts positive, crosses 0 exactly at x equals e, and then becomes negative. A continuous function can only do that if it crosses the axis exactly once. So let's wrap this up. This equation that looked pretty nasty at first turned out to have a beautiful, unique solution. Through algebra, numerical methods, and graphical intuition, we've seen from multiple angles that x equals e is the one and only answer. Thanks for watching. If you enjoyed this, consider giving it a like and subscribing for more explorations in mathematics.